Welcome to the House of Maths. Here's my next vector question. This time we've got a different shape. The last one's been looking at triangular shapes. This one is clearly not a triangle, although we do have triangle shapes within it, but it looks like a trapezium, doesn't it? So we've been given some information. We've got some of the vectors labelled for us. This time they're given as there are two parts to the vectors. All of them have got two parts. So 2a plus 3b is this vector. S to r is 3a plus b, and S to q is 4a minus b. So the first thing we're asked to do is find PQ in terms of A and B. So we want P to Q. So remember, on the diagram, you're looking for a route from P to Q using vectors that you've got. Hopefully you can see that you're going to go up here and down here. So you're going to be using these two vectors. So PQ is going to be found by going from P to S. So vector PS plus vector SQ. So let's put those in. PS is this vector here. So that's 2a plus 3b. And we've got to add to it this vector here, 4a minus b. And then we can summarise those. We've got 2a here plus 4a here. That's going to give us 6a. And then we've got 3b minus b, which is going to be 2b. So vector PQ is 6a plus 2b. So let's put that in. Let's label that on our diagram. That is 6a plus 2b. The next part of the question says, show that PQRS is a trapezium. Well, it looks like a trapezium, but that's not going to be good enough to prove it's a trapezium, because the diagram could not be drawn to scale. This line could be sloping down a little bit or up a little bit. You can't just say it's a trapezium because it looks like one. So what we need to know is, what are the features of a trapezium? What's the main thing that determines whether it's a trapezium? Well, it's got to have four sides, which this one certainly has around the outside. But the main feature is that this line and this line are parallel. That's the key thing. So if we can prove that PQ is parallel to SR, we can prove that's a trapezium. Okay, so what I'm going to say is that vector PQ must be parallel to SR. Now, as far as vectors are concerned, one vector is parallel to another if it is a scalar multiple of that vector. Okay, so I'm going to put that down. So we're saying one vector must be a scalar multiple of the other. So can we show in this case that this vector and this one are scalar multiples of each other? Now I think we can do that. We've got SR is 3a plus b, and we've got PQ, which is 6a plus 2b. So what we can do here is we can factorise this vector here. So if I take a factor of 2 out of this, I am going to be left with 3a plus b. So if you think about multiplying out the brackets, 2 times 3a is 6a, 2 times b is 2b. So if you look at these two vectors, so this is still PQ here. If you compare PQ with SR, they've basically got the same vector, 3a plus b, 3a plus b, but this one's just been multiplied twice. So when we talk about a scalar multiple, we're referring to this. This is the scalar multiple. A scalar is something that just has size, in this case 2. So this vector is in fact twice as long as that one, and they are parallel to each other because they are multiples of each other. In other words, 3a plus b, 3a plus b, then that proves that they are parallel to each other. And that's the crux of this question here, proving that one is parallel to the other. You need to show that it's a scalar multiple, and that is sufficient to prove that it's parallel. Okay, hope you enjoyed that. There'll be another one coming soon.